Hello, happy Friday. Welcome to another Lunch and Learn sponsored by the Tampa IIBA. This week it's about what business analysts might want to know about software. So I've been doing simulation for a long time, and that taught me all these skills that business analysts do. Plus, since I often or almost always worked with customers as a consultant or vendor, I had those skills and I did all the hardcore data analysis, software engineering, programming, testing, VB&A, and the whole life cycle. So I've seen this all from every angle. I've done it in a lot of industries, in a lot of locations all over the world, for a lot of different architectures and for many different applications. So I can tell you the methods that you're taught as BAs are very general and they're really widely applicable. That doesn't mean there aren't specific things to learn in every industry or whatnot, but it does mean that you bring a formidable and usable group of skills to your activities, no matter where you go, if you're an experienced being. Just a couple ground rules here. These presentations are all on my website, rpchurchill.com. They're on the portfolio page under presentations. Anytime you see orange in this presentation, it's in the reveal.js framework. That's a link, so you can follow that to read more. Sometimes it'll point to Wikipedia, sometimes it'll point to longer articles I've written in my blog, and sometimes other resources. So that's always there for your reference. So, you know that computers store information as ones and zeros, and there might be a lot of different ways it does it. There can be many numerical types, there are logical types, character types, and they can be put together into different structures, arrays, strings, records, objects, and so on. Objects are interesting because they combine data and also subroutines, so its actions are bound with the data. And sometimes, uh, depending on the language and the power that it lets you have, you can do really complex things with memory. You can overlay variables. Um, it's better if you know how to pack them so you can save space. And there are a lot of other considerations there. So at root, computers can only do 6 things. And in reality, they can only do 3. And there are 3 additional kind of meta operations. So everything a computer does involves moving data from one place to another. That means I/O, and it means moving stuff around in memory. It can add or subtract two numbers. That might not seem like a big deal. And it can do what I call bit twiddling. So that means it can shift all the bits one way or another. It can mask them, it can invert them, it can do logical operations, and it can check status flags. Everything else you do on a computer is a combination of those operations. So, multiplication, for example, is just a series of adds and shifts. No, the meta operations have to do with the instructions. So every time it does an operation, in most cases, it simply jumps to the next instruction, and it knows based on the processor in the instruction how far to jump ahead in memory. It can also jump to a different instruction, as it'll do in a go to a subroutine or other structure, which I'll get to in a minute, or it can just stop that particular process. So everything anybody does is basically these 6 operations. So how do computers operate? At the machine level, there's a BIOS, or basic input output system. It's generally stored in some kind of ROM. It's a series of instructions that bootstrap the OS, know how to talk to some of the um, hardware devices attached to the computer, like disk and so on. And it's very basic. When the first computers were put together, people had to do everything by hand. They had to set the individual ones and zeros by switches and literal hand switches. So the BIOS is generally written in assembly language, in the language of the particular chips. At the operating system level, that's written in a low-level system language that gives access to the rest of the hardware, provides background services, and allows users to start applications and so on. The application level on the computer is the next level of complexity. That's where we operate as beings. That's where the computer actually does the specific things that are useful to the user. Then you get to higher level groupings where multiple computers are working together to create unified systems that do one or many things at scale. And then you can have clusters of clusters, but the point is made. So there are languages on the one hand, and there are also programming tools to manipulate those languages. And that's what we're talking about here. So a programming language in general is just a way to translate human readable code into a form that the machine understands. It automates generating this code. It reduces errors. It'll, for example, help you write the structure. For example, if you do an open curly brace, it'll write a closed one for you. If you start typing a keyword or a variable, it'll offer suggestions to finish them for you. And it does automatically a lot of the things that good programmers did by themselves. It can integrate reference material, help with debugging and testing, help you manage large projects, enhance collaboration, people working together in general, help you manage larger projects and more complex projects in terms of scope and scale. So every language, and I've worked more or less with about 18 different languages. Um, some I've just taken one course in, some I've worked at full time for 8 or 10 years at a time. I took my first programming courses or course 40 years ago this spring. Um, so and there were a lot of different kinds of reading and writing with many different kinds of devices, math operations, and also assignments. So when you're moving data from one place to another, that's basically a math operation. String operations, creating new variables and deleting them. There's a difference here between static and dynamic. With modern programs, everything is dynamic. There is no fixed data segment, but older programming languages do have a fixed data segment. If then else and switch conditionals, that is, you do some kind of a logical test. Is this bigger than that? Is it less? Does it match or they equal? And then either do the next thing or jump someplace else. There are different kinds of loops. One is simply do it X number of times you specify, and there are tests at the top and tests at the bottom loop. Tests at the top you may not run through ever. If the test condition is false the first time, test at the bottom, you're gonna run through once at least. There are jumps and go-tos, like I said a couple slides ago, and there are subroutines. Everything else is just a combination of those things. Like I said, I've studied 18 different languages, and learning every individual language is pretty simple up front. In the end, the isness of every language comes less from the language itself and more from the libraries and application frameworks and development tools you need to learn. So there are different characteristics of languages. that drive why they are chosen for use in different situations. Also, different languages bundle data items together in different ways. Some allow you, like I showed you on the first page, to have all kinds of data types and they're very complex. Some take that power out of your hand and say, I'm going to give you one number type and we're going to make it simple. There are benefits and costs to doing that, which we'll get to. So types of languages, there are many different kinds and not going to give you an exhaustive discussion of these, but we'll concentrate on the top ones. Construction languages are a lot of what we actually work with as BA. And we don't work with them directly, but we work with the people who are using them to implement the vision and solve the problem that we're trying to address. So a command language kind of works at the operating system level. A configuration language works at the same level or at the application level. In the application itself, the programming languages are used to write those and operating systems, but most of the work we're concerned with is things that are implemented using programming languages. So over the years, there have been several generations of software. The fifth never really happened. They found that it's a really hard program or really hard problem to solve, and people are working on it, but they haven't cracked that nut yet, and it's been 40 years, so it's really hard. The first generation, like I told you, is programs written in ones and zeros at a really low level. They weren't that complex. Then we had essentially assembly languages. And then we got application languages, third generation. Those are most of the languages we know. Fourth generation languages are more specialized. They may have slightly different formats. They automate a lot of things. They can be graphical, they can be low code. That's really where a lot of the new action is, and they're built on third level things. BAs may work with programmers working in 4GLs as well as 3GLs. Also, there's an article here on programming paradigms. I won't go into that in detail. I'll tell you there's a link on Wikipedia which has a very long discussion and a lot of additional links you can follow. So I have a question for you. If you're gonna put together a program, is it more important to optimize on speed or memory usage? And the answer is that it depends. So there is no one answer, and these aren't the only two considerations when you're optimizing a software system. So, like I said, newer tools take more work out of the hands of programmers. Now, the benefit is that it speeds things up, it reduces the errors, and it makes things simpler. The cost is you lose control and you need more computing resources. So you're basically throwing hardware at a problem, sometimes a lot, and but that's really cheaper in the long run. So what are some examples? Old languages, you had to manage everything in memory by hand. With fixed declared memory items or data variables, it wasn't a big deal. You start the program, set up the memory you want, it never changes, and everything's cool. With dynamic memory allocation, things get real complicated real fast, and that's a giant source of errors. I also mentioned uh, simplified data types instead of many different types. They say, okay, you're only gonna get one now, and you're gonna be happy, and you won't have that complexity. Compiled versus interpreted languages, or and there are gradations between these, or it can be more flexible and used in more places, but there are trade-offs with using them. You lose some low-level control. You can't do some things in higher level, more abstract languages than you can in lower level system languages. But again, that's to keep you from making mistakes. So we're trading off in a lot of areas. Here is a list of things we can trade off in all our different areas. Um, I'm not gonna discuss them in a whole lot of detail, but I'll say that the ultimate end is to minimize the total cost of ownership of a system um, over the entire life cycle. That's really the goal. You know, definitely have heard about the iron triangle, which makes you choose between quality and cost and time, basically. The joke is make it fast, cheap, or good, pick two. And if you want it really fast, really cheap, or really good, pick one. Now let's talk about communication. When I was in an Army leadership school, I learned this simple communication model. So it's what the speaker thinks was said, what he or she actually said, what was actually transmitted, what the listener actually heard, and what that person thinks was heard, and how they interpreted it. So this comes into play in a lot of ways. Um, Now, this process can be mitigated by being clear in the first place, and also by error checking mechanisms. So ideally, you have a two-way conversation where you say the thing you want to say, and then you check in with the listener to see if they heard it correctly, see if they agree, and then you go back and forth to try to work out until you get some kind of agreement. Every kind of communication that's effective uses this process in some way. So, your encoding and decoding by the speaker and listener can be improved by review, mutual expertise, patience, and empathy. And the middle blocks can be improved by improving the communication channel itself. So if we're going to have computers talk to each other, let's look up here. Um, so they go through a process of encoding where they put together all the elements of a message. Then they establish the communications channel. They connect with the remote process. Then they send the message. So that's like what the speaker said, and establishing a connection and what the speaker actually said. Then there's what's actually transmitted. Then there's you get it, you unpack it, and you interpret and validate. There are specific communication protocols for all kinds of communication between computers. There are serial ports, parallel ports, network ports. TCP/IP is what the internet is built on. There are other communication protocols that sit on top of all those, like HTML and XML and various media, audio, video, picture formats, and so on. So eventually you have a two-way conversation where you're packing and unpacking these um, messages and verifying them to make sure that you've got all the information right. So don't assume this just works. You wouldn't do it in your personal communications. Now, the details of this may not be your explicit job as a BA, but you should help make sure the programmer is doing. Part of dealing with communication is arranging for retries, log everything if that makes sense, and everything else I've said. So as a BA, how do we do communication? I talked in previous sessions about my framework for doing business analysis, and it goes through these steps. And that mirrors the steps you go through in the BABA, but it's in my own language based on my own experience. So if you're talking to a customer, that communication is improved by mutual expertise, patience, and empathy. Um, Same thing is true when talking to users. The expertise may be a little bit different, but the patience and empathy is the same. And the same thing happens when you're talking to a technical team. If you notice a pattern here, good for you. The same applies to talking to management and external entities. They all have their own expertise required to talk to them. Documentation, review, feedback, and correction are human forms of error checking, queuing, and retrying. So, what this diagram is saying is you go through cycles of figuring out what the whole project's going to be, and you go around and around until you agree, and then you go to the next step, which in this case is figuring out what's going on. And you go around and around and back and forth until you all agree on that. And if you find something new, you might go back a step and add or change something and then go back to the current step. And you do the same thing with requirements and so on to the end. So the communication process is about the same in every situation. Wikipedia lists close to 60 possible non-functional requirements. I know of a few more I could add to that list. Um, those are qualities and solutions should have. Now, um, ideally, everybody in any engagement or project you're working on will be working to identify these. But as a BA, don't be bashful about making people think about it explicitly. User interfaces should clearly display information. They should enable effective control that should be efficient and intuitive. They help the user always know what's going on, what's been done, and what needs to be done, prevents errors, and helps recovery from errors. The other thing is, if you've established everything that's going on in the conceptual model and in the requirements, user interfaces should, as a utilitarian matter, practically write themselves. Then it's just a question of doing it with style and panache. But the function of the UI should be clear. So I've used really good and really bad ones. Some are really good at telling you where you're at, what you still need to do, and some aren't. There are a lot of things you can do to design UIs and that make you do the right thing. As BAs, you should have a good understanding of UIs and be able to know what they are, be able to draw them out and talk with users and developers about them. Then the question becomes, how many ways are you going to allow users to do things? We all know that users respond to information and they absorb information in different ways. There are a lot of ways to do user interaction, menu commands, ribbon commands, push buttons, speed buttons, keyboard shortcuts, and other things. Then we talk about accessibility for the disabled. Um, as it happens, the Tuesday after next, on the 16th of this month, is going to be the next IIBA webinar. It's going to be online. I highly encourage you to sign on board. That's going to be a good one. It's in the evening. I'll be back in 3 weeks. So, given some of the discussion of things going from low level to high level over time, we see that the trend in software is toward greater abstraction, and that supports greater productivity and complexity. And that's really what it's all about. All the technical decisions that um, programmers, developers, and managers will make is ultimately to lower the total cost of ownership of a project or engagement or system. Finally, there's no one best way to do anything. Everything is really all about negotiation, trial and error, feeling your way through a process and coming up with the best solution, given the time and resources you have. I want to recommend a book to you. I don't know if it can be found in hard copy that easily anymore, but what it talks about is that the same thing has been going on in commuting for now it's really 70 years. The book's kind of old. Um, And it says that, every new invention that comes along in commuting, everybody says this is going to fix everything. And it applies to every problem, and it really doesn't. It makes a meaningful advance in one small area, and it really represents overall an incremental advance. And that's been true forever, and it's probably gonna be true forever. So any true believer who says they have the one final answer for how things should be done, they're probably a little misguided. I appreciate their enthusiasm. I've seen a goodly section of this. I really talked about communication so much because that's our job as BAs in every other role to really talk about all the details, and that is really the killer app. And that's all I have for this week. Thank you, everyone. And like I said, Tuesday the 16th in the next session. And thank you very much. Have a great weekend. Thank you. All these slides are on my website, so have a look. Let me know. Oh, by the way, there's one more slide. That's how you find me. There we go. Cliff, anything?
Nope. Happy Friday, everyone. Have a great weekend. Bob will be back in 3 weeks, and then we have a night event coming up in 2 weeks.
The recording and the links to these slides will be on the website shortly on the meetup page, and they'll be on my website also. So thanks, everyone.
Thank you. Have a great weekend.